Okay, welcome friends. Welcome to the outreach program of IIRS. Today's lecture is on remote sensing application to atmospheric studies. So, what constitutes the meteorology? So, first of all, we'll understand that meteorology is not only the study of science of various aspects of the weather and the climate, but also it's a study of the physics and chemistry of the Earth's atmosphere, including its interaction. You see the interaction between the atmosphere and the surface, including the land and ocean. And also, meteorology describes the atmospheric composition, structure, different properties, then motions in the atmosphere. And why do we require to? This also helps in monitoring of the day-to-day weather and in long term the climate, but also in the forecasting and try to understand the nowcasting features. So we have the weather monitoring and observations, the modeling aspects which helps to forecast and helps to predict in the near future. Now the what are the parameters? So there are certain parameters. So because as you know that the weather is to understand is the current state of the atmosphere, and climate is the long term state of the weather. Therefore, there are certain factors or certain parameters which determines the state and condition of the atmosphere. These are basically the temperature, humidity, winds, then cloud, also the radiation profiles and the cloud or the rain. Now the atmosphere has different atmospheric layers, so they have different physical properties, and these are determined by these above factors which I described. And this also helps for not only the monitoring but also for the forecasting. And for forecasting, basically these observations helps to use in the forecasting models, which are basically a set of equations which depicts the state of the atmosphere. And these models also use the ground data, and with the advent of the satellite data, this helps to assimilate the data, better assimilate data for better accuracy of forecasting from the atmosphere, from the satellite data. Also, there are aerosols and the greenhouse gases, which also is a part of the atmosphere. And to understand the pollution or the air quality, the understanding of or the observation of the trace gases and the aerosols is much need of the hour. So in the nutshell, this is the atmosphere. You very well know that in the atmosphere there are constant gases, the trace gases and variable components. Nitrogen, oxygen, argon, these are the stable gases which have definite proportions. You know that percentage. I will not go in detail of that. There are trace gases. There are very small in number, but these are mostly anthropogenic generated, and then from decades to decades, these the percentage or the concentration of trace gases varies. Also, there is variable components which aerosols and water vapor come into picture, and they are so variable that from it changes from place to place, from region to region, and that's why the monitoring observation of the variable components as well as trace gases is important to understand the pollution or the air quality. From the perspective of the satellite data, we have two classes. You know that very well know in the other classes also you had through this medium that the classification is passive and active. Passive uses the sun source as the main energy, which helps to understand many processes. So in the passive, we have the optical remote sensing and the passive microwave remote sensing, and in the active we have lidar and radar. So what do we measure? So when so in remote sensing, whenever the electromagnetic radiations interact with the atmospheric constituents, so the larger particles scatter, that is a scattering process, and the smaller particles, that molecules or gases, they absorb, and the absorption occurs when the molecule or the atom has the same frequency, which is known as the resonant frequency, as the incident radiation. So from these scattering and absorption, the properties of the atmospheric constituents, that is whether it is gases or aerosol, then we calculate the number of properties like the density of it, the number concentration of various atmospheric gases, using physics law, that is Lambert-Beard law, famous Lambert-Beard law, and when it interacts with the material, that is the atmospheric constituents, so basically it interacts with in terms of intensity, the polarization and angular distribution. Now now in the whenever we know that there are certain atmospheric windows through which the sensors senses the radiation from the earth's surface, whether it is emitted or it is reflected. Now as I said, the gases, the molecules, they absorb atmospheric that is electromagnetic radiation, and this helps to understand the concentration of the atmosphere of the gases in the atmosphere. Now we say that these are certain these are absorptions of certain atmospheric constituents. So we have water vapor, ozone, methane, carbon dioxide. So these are absorption spectra or absorption fingerprints, and whenever the sensor at the satellite's level senses this and there is a absorption band in this particular wavelength, then we can indirectly find out that this is the carbon dioxide or certain atmospheric constituent, and the width or the strength of the absorption gives the concentration of it. So in the nutshell, if you see that the specific gases or the constituents, atmospheric constituents, has different atmospheric or the absorption bands in different wavelengths. So in the optical remote sensing, in the thermal infrared and in the microwave wavelength. So water vapor, mostly it is in optical and in the microwave also. That is the oxygen, then carbon monoxide, that is in the in thermal infrared region, methane, absorption bands in thermal infrared region, carbon dioxide, we have one in optical and strong in thermal infrared, nitrous oxide, tropospheric ozone or ozone, nitrogen dioxide, SO2. Now as I said, the trace gases, there is trace gases use the signature of the absorption, that is the fingerprint of the absorption spectra. Though satellite detect that backscatter solar radiation or emitted solar radiation, backscatter from the ultraviolet or visible region and emitted in the infrared region. So both these signatures, the gases have a specific signatures of absorption spectra. So once try to tap this distinct spectra of each gas and tries to understand the or estimate the concentration in the atmosphere. So all the satellite remote sensing measurement of the troposphere are based on the interaction of the electromagnetic radiation with the atmospheric constituents. Now if you see in the ultraviolet region, that is backscatter, the energy what is received at the that is satellite level is a backscatter from different layers of the atmosphere. So Rayleigh scattering is most important here, because the majority of the photons are scattered from the lower atmospheric, that is lower troposphere region before it reaches the surface. So because it has a large intensity, strong intensity, and that's why it has a large signal to noise ratio. And then in the visible also similarly, it has also the more scattering or more Rayleigh scattering is from the lower part of the troposphere. In near infrared, the scattering is little relevance and emission is also weak. So hence the emission and the energy what is coming from the, or the interaction which is happening from the atmosphere is homogeneous in all layers. So this gives the total columnar concentration of a particular gas. In infrared or thermal infrared, so it is most basically the emission, and this emission different layers, that is the lower troposphere or the middle troposphere or the upper troposphere, they emit the thermal emission, and this emission reaches at the satellite level, satellite sensor. So this helps to understand the different constituents at different layers. So this is basically the vertical sensitivity, with the vertical distribution of the atmospheric constituents. Here you can have only one or two levels, the concentration 1 or 2 levels, or the total columnar levels, because the scattering is more, or the absorption is more in the lower troposphere than in the middle or upper troposphere. But here in the infrared emission, almost all the layers emit, and the information from these layers is gathered, and which is back converted to get the concentration vertical profiling, or we can say the vertical profiling of the particular gas we can find. And this is also known as, this is most importantly principle used in the atmospheric sounding techniques, where we have sounders in the satellite level, and which looks vertically to estimate the vertical profile and determine the physical properties of the atmosphere. So whether it is a temperature, pressure, or it is humidity, or the concentration of different gases. Now if we move to the satellites. So as I said, there are two types of satellites. One is geostationary and the polar orbiting satellite. Now in this, what happens is, in the geostationary satellite, that is 32,000 kilometers, we have in the geostationary platform, which is at the 36,000 kilometers. So we have different satellites. This goes on the US satellites, Meteosat from the Europe, Japanese meteorological satellite, that is geostationary meteorological satellite, Japanese GMS, and our Indian INSAT satellite. And from this, they have from this 36,000 kilometers, the temporal resolution is very high. That is, every half an hour to 15 minutes, we get the information over different parameters, which we have discussed earlier in earlier slides. And these are some of the products or the information, that is the outgoing long wave radiation. That is, we know that there is short wave radiation coming from this solar that is sun, and this is outgoing long wave radiation which is emitted from the Earth surface. So these should be in equilibrium, but due to the various aspects, like for example the variation in the cloud formation or in the pollution like dust and other things which is happening in the atmosphere, the the balance is changing. So there is a change in the outgoing long wave radiation, and which is this monitoring of OLR is important to know the balance, that is the balance in the atmosphere, as well as the albedo, the cloud albedo. And this is also widely used for knowing the rainfall or the forecasting of the rainfall. That is the rainfall estimation, that is the quantitative precipitation estimation. So rainfall can also be directly, indirectly measured or estimated from the satellite sensors. So basically, by combination of the visible and infrared radiation from the sensors, one can estimate, knowing the type of the cloud or the cloud temperatures, that is the bottom cloud temperature or the cloud top cloud temperature, and using the empirical statistical relationships, one can estimate the rainfall. Then the sea surface temperature, that is the temperature of the oceans or the sea. Then cloud motion vectors, say due to the winds, how the cloud moves, and then the rate of the movement of the cloud and the direction of the clouds also be estimated, and this helps to further estimate the rainfall. Then upper tropospheric height. So this is an important climate variable because it has a significant impact on the earth radiation budget, and this is associated with the water vapor feedback, which applies to the climate response or the earth's climate response. Then the snow cover, the fire, whether it is a forest fire or a stubble fire or any kind of fire, smoke, the aerosols, that is the larger particles, like you have that is particulate matter PM10 and PM2.5. So aerosol can be estimated directly using the physics of it, and then this can also be helped to indirectly measure the particulate matter. Of course, the gases, as I said, the cloud mask, and so on. There are the other parameters also. Then also we have the polar orbiting satellite. In the polar orbiting satellite, which has a sun synchronous satellites, and it has a global coverage. Geostationary has a regional coverage. This has a global coverage. And to name a few, I have listed here: GOM, MODIS, MISR. So these are the sensors which are used for the study of the trace gases and aerosols. Of course, in that the fire and other smoke, other components are also embedded in that. I have listed here: radiation budget, fire, smoke, trace gases, aerosols. And then there is another kind which I said, sounders. So which gives the vertical profiling of the atmospheric layers. So this is IIRS, that is the high resolution infrared sounder. So it has, so these are above are the multispectral channels. So around 4 or 5 or 6 channels only we can have, and we have to sense in these channels. But here we have numerous channels. For example, this has 20 channels. IIRS has 20 channels operating in 3 to 15 micrometer range, and this provides vertical profiling of temperature, humidity, winds, cloud height, and so on, albedo. ISI, that is this is the ERC. This is a hyperspectral infrared sounder. This has more than 2000 channels. IIRS, atmospheric infrared sounder. This has more than 2300 channels, and by so many channels we can have a high vertical resolution, saying that so many layers or so many vertical heights we can have information over many parameters, including the gases. So this measures not only the the temperature, humidity, winds, but also the gases like ozone, carbon monoxide, carbon dioxide, methane, and so on. The cross-track infrared sounder, this has also more than 2000 channels, and this also similarly used for profiling of different gases and atmospheric parameters. This geostationary, as I said, goes and inside is geostationary, but here also we have a sounder, infrared sounder, but there is a multispectral sounder which has 19 channel sounder. This has so many thousands of channels, but these are hyperspectral sounder which are also used for profiling it, but the vertical accuracy, vertical resolution is not high as the infrared sounders. Also there is a microwave sounder, so which is known as advanced microwave sounding unit. So these are operating in the microwave range, that is 20 to 90 gigahertz, and the beauty of it is because it is independent of the clouds. So so the temperature profiling or the other profiling can be done even in the cloudy conditions also. So this is just the a glimpse of the coverages of the geostationary satellites. So Meteosat, INSAT, Japanese, the global monitoring satellite, goes. So they have East Pacific and the West Pacific, goes R and goes, that is the West and East of the US. These are some of the glimpses of that is the sounder, ERC. The sounder, this is total CO columnar concentration of carbon monoxide, ozone. Then we have the formic acid, the methanol, then the nitric acid, ozone, ammonia, SO2, and so on. So many there are numerous the gases which can be estimated from the sounders, infrared sounders. So another example of the infrared sounder, where the near real time plume, suppose there is an accident fire or there is a plume from one region to other region, so we can track it, we can know the rate at which the plume is moving and in which direction. So that can also be assessed from these types of sounders. This is some of the glimpse of the sensors which are used for, and these are the properties, that is for the trace gases, aerosols, and the energy budget studies. So we have, these are many of the polar orbiting satellites. So Tropomi, MISR, Ceres, MODIS, MOPIT. So these are used for the cloud, the aerosol, the trace gases, and different energy budget studies. So INSAT 3D and 3DR has both the same configuration, only these are two tandem satellites. One was launched in June 2013, another in 2016. So it has 6 channel imager and 19 channel sounder, as I said. And these are a few the products which I described in the earlier slide, that outgoing long wave radiation, upper tropospheric humidity, rainfall, sea surface temperature, cloud mask. So these are the products which are also given directly to the users. So one can use directly the products and for its hazard own research applications. So these are the vertical profiling. This is the sounder, vertical profiling, the pressure, elevation, temperature profiles, water vapor profiles. So this is the cloud motion vector or wind. From the motion from the wind, one can the clouds, how the clouds move, and then we can understand from point A to point B and the traveling time and the traveling location. We can also find out the speed of it, and then we determine the wind speeds of the at different levels, at different atmospheric levels. This is glimpse of the precipitation index. That is 3-hour consolidated rainfall estimate. This is the sea surface temperature from the INSAT 3D. And like this also we can get every half an hour we can have rainfall data. So every half an hour, 30 minutes, 3 hours, or daily, as the composite of all scenes composite together, and we estimated the daily rainfall. So these are being converted and given to the public by IMD. Now this how do we how do we interpret it? So what happens is this is the visible, that is the visible channel. As I said, the INSAT 3A or 3D, they have visible infrared and water vapor channel. This is the visible channel. And so in this we can see that it is a black and white. So white we can see that these are some clouds, and black we can see water, and grayish color we can see as the land. So here the objects with the high albedo looks brighter. So like clouds, they look brighter than the water. So easily we can identify the clouds, the land, and the water. So these are easily discernible. So the high clouds and the low clouds also we can see according to the reflectivity or the albedo of the clouds. Now in the infrared, we don't get reflection, but it is the emission. So that is each and every object on the ground surface as well as in the atmosphere, they emit radiation, and this emission is being captured from the satellite level. And so in other words, that is, if we convert the emission to temperature, so in other way we can say that at the satellite level we measure the temperature of various constituents in the atmosphere as well as on the land. So we can see that now the important point is, if the object has a low temperature, so it will be having black in color, the low color. For example, here clouds will have low temperature as compared to the land and water. So basically, if temperature is high or temperature is large, it will look brighter. But as we know that we have a visual tendency to see clouds in white color, so we invert this temperature image. It means the low temperature will look brighter and higher temperature will look darker. So this is, we invert these images. So now this is an inverted temperature image or the emission image of the infrared imagery. That is, the brighter, that is the clouds are having low temperature and land or water has high temperature. So here we can see that the coastlines, that is the water and the land, is clearly separable, and also the clouds, we can see that these are easily identifiable in the infrared image. Now in the water vapor image, which is around 6.7 micron, so this is the water vapor absorption channel. So it detects the moisture content in the middle and the upper troposphere. Now as I said, that infrared and water vapor channel, they are inverted images, because as we know that, as I said, that we have a habit of seeing clouds as white. So this image, water vapor image, also is inverted, and the brighter colors or brighter objects are having low temperature or having high moisture. This is inverted. Actually, high moisture should have low temperature, so that should be looking like a dark. But here, if we have inverted, it means the brighter objects not only has the low temperature but also has the high moisture in it. So cloud, as we know that clouds have high moisture. So different types of clouds, that is the middle level clouds or the high level clouds, also we can distinguish from the moisture content, and this helps to understand the clouds, and then this also helps to interpretation and the information on the rainfall. So in totality, how it looks, the visible, you see, we can see that in visible. So in that visible, we can see a part of the land as well as the clouds. In the infrared also easily identifiable because the emission from the land, ocean and the clouds. But in the water vapor, we only the moisture, that is the moisture in the atmosphere, it only enhances, and we see mostly the clouds or the moisture in the clouds. So in visible and infrared, we can see land but not in the water vapor imagery. Just a snapshot of the INSAT 3D. This is the visible image. The second one is the shortwave infrared image. The third one is the middle infrared, that is 3.9 micron. This is third one is 3.9 micron infrared image. Second one was shortwave infrared, that is around 1.6 or 1.7 micron. Then this one is the water vapor image, and these two are thermal infrared in the longer thermal infrared, that is 11 to 12 microns. So we can see that in the visible image, we can easily identifiable the that is the grayness of the land, ocean and the clouds, whereas in the middle in the shortwave infrared, the enhancement of the that is the desert or the moisture or the dry areas also we can see. In the middle infrared, that is around 3.9 microns. So easily we can identifiable the clouds and the other cloud properties. Here the types of the cloud also we can identifiable in the because of the moisture in the water vapor, and this is the temperature images in the longer thermal infrared. Also important property we can also see on the tropical cyclones. So you very well know that it is basically a horizontal scale around 1000 kilometers that extend through, and there is a deep depression happens because the high humidity and the sea surface temperature of more than 26 degrees centigrade are the major contributing factors in the ocean, and then water evaporates from the ocean surface and comes in contact with the cold air, forming the clouds, and a column of low pressure develops at the center, and wind around that column forms in a high pressure area, high winds, and this can be also easily identifiable from the satellite observations. This is some glimpse of the cyclone in 2019. So the movement of the clouds in infrared sensor as well as in the visible sensor. So similar explanation is also given as we have discussed in the clouds and other formation. So the wind speed, the cloud formation also we can see, and also we can see the forecasted in next 12 to 72 hours where it will strike, depending on the trajectories of the clouds and the winds. One can estimate the strength, the where it will hit on the land. That also we can be estimated. So this is the IMD gives a forecast of it, and the observation and the forecasting of the cyclones. Another important property is the fog. Actually, because there is our life is dependent on many of the things on the transportation sectors, and the fog, the formation of the fog and other things, they jeopardize the movement of the road, air and the shipping routes, and which has hinders the societal and the economic importance or the economic of a country or a region. So that's why information on fog is also important. To the monitoring and prediction of the fog is also important. So in that, the satellite data gives an important input in the monitoring and also the forecasting of the fog. So daytime fog and nighttime fog also can be predicted and be forecasted. But the algorithms are entirely different. In the visible in the daytime, visible bands are used for monitoring of the fog, whereas at night there is no visible band, so you have to rely on the infrared bands, so infrared region. So a dual channel difference or the some brightness temperature difference methods are used to, that is infrared band 1 and infrared band 2. These are used in different algorithms to estimate the fog in the night time. Of course, the air pollution is important aspect, and then you know that the atmospheric aerosols, these are the larger emitted particles, either from the natural source or from the anthropogenic sources, and this affect not only the public health, that is health, children or the women or any species, but also on the visibility aspects, the ocean fertilization, the changing in the atmospheric chemistry, the cloud formation, and also ultimately the climate forcing. And these are the main sources of it: the vehicular pollution, power plants, refineries, biomass, and the burning. So from the, this is a glimpse of inside 3D. So the parameter known as aerosol optical depth, this is an indicator of the pollution over area, aerosol pollution over an area, and one can, every half an hour we can estimate the aerosol optical depth, which is an indicator of the pollution. This also we can see as compared to the fire. For example, during the October-November we have a stubble burning in Punjab and Punjab-Haryana region, and this can also be associated to the pollution, and one can see what is the level of the pollution which is governed by these fires and how it spreads from one region to other region, particularly over the NCR or the Indo-Gangetic plain. So these kinds of studies and these kinds of information can also be obtained from the satellite data in a real-time mode. So this is the MODIS data, that is a sun synchronous satellite, and also this can be INSAT or geostationary satellite can also be used to infer these informations. So then one can develop from the AOD the PM10 and PM2.5, and detailing of it can also be done. So for example, these studies, this is the INSAT 3D image of one such date in October-November stubble burning, and so much of spreading from the Punjab and Haryana and across the international boundary. Also we see that lot of plumes from the stubble burning enter because of the steady wind flows and the direction in this in Indo-Gangetic plain, that is the eastern Indo-Gangetic plain, and this hinders or this alters or this makes the poor air quality over northern India, particularly on the Indo-Gangetic plain, NCR and other regions. And this can also be monitored, or it can be validated on the ground instruments, what is the air quality, and then this can be used for the modeling of the forecasting of the air pollution modeling. Thank you so much.